I had a question about the number 4 on the test, where it said S is the surface of B2. Is
Mhm.
B2 just like the box of size 2?
I discussed what B was. It's a ball.
Ball size 2? Okay. That's like centered at the origin.
Yes.
Okay. Thank you.
It's a bold B, right?
Yeah.
Yeah. I'm gonna look through them today at my office. Happy Tuesday. I think we said we're going to just jump back and forth between Stokes' theorem and divergence theorem problems. That we'll do a Stokes problem, then we'll do a divergence. Then have Stokes do another divergence. Hopefully we can get through those problems today. If not, well, we'll just finish it up on Thursday, whatever, no big deal. Did I sign the divergence and Stokes homework yet on my open math? Then that'll be today. At the end of class, I'll post those as well. All right, quizzes have been posted. You should have gotten those alerts. Obviously, the test, right, due Thursday at 11:59. For all of these Stokes problems, we're going to be calculating circulation over the given curve. So we're calculating circulation of 2y 3x negative z squared along the circle x squared plus y squared equals 9 located in the xy plane. Oriented counterclockwise when viewed from above. I did spell that right. I just don't think I copied it. Yeah, to include the E in the copy. We need the curl. Which is great, because I was going to do curl anyway, see if it was conservative. Because if it's conservative, I'm done. 0. I can just look at this and tell you it's not conservative. Partial y, partial z, partial x. No, partial z, partial x is 0. Partial x minus partial y is 1. So close. Yet so far. But at least that's a nice curl. We need to parameterize the surface. It's actually what we're dealing with here is just the surface of the circle, which is nice. Normal vector. Again, should be fairly obvious. Dealing with normal vector 0, 0, R. Bless you. And that is outward pointing. That is positive orientation. Now we're dealing with this surface integral. Like the curl along the parameterization. Now that's nice because curl is a constant. ds becomes the normal vector dA. This is what we have.
You have to multiply by another R because you're changing the polar.
I'm not changing the polar, am I? The parameterization is R theta. However, recognize that is a polar area integral.
What do you mean you're not changing the polar?
I'm not converting this to polar coordinates. No, that's my parameterization. Just how I parameterized it, so it's not a conversion into polar. Conversion to polar is if I set it up rectangularly and then wrote it in terms of R theta. Which you can do, by the way. And if you set this up rectangularly, you're going to get, what is it? Integral from -3 to 3, integral from -√9 minus x squared to +√9 minus x squared of just dy dx. Which is this when you convert to polar. That's a polar area integral. So it's just the area of our domain. Nine pi. This should be number 4, right? I think that's how I had it numbered. I think I called this, what, number 2? Yeah, so this should have been number 3. Find outward flux across the given surface. So the surface is the cube bounded by the planes plus minus 1 for x, y, and z. Right. So this is just shorthand of saying x is plus minus 1, y is plus minus 1, z is plus minus 1. Notice we could have also written this. Right, the cube minus 1, 1 cross minus 1, 1 cross minus 1, 1. Same thing. Well, if you were to do this without the use of one of the theorems, we actually did a problem like this, right? There's 6 surfaces you have to examine. Again, each one's not too complicated to parameterize, but it is tedious. We now have divergence theorem, which is going to make this problem much easier. Let's first find divergence. Divergence is -2. W. You know what? I'm just going to move it. W is just that cube. So outward flux, right? Remember, is just the surface integral of the vector field along the surface with positive orientation, outward pointing normal vectors. Outward flux is just the surface integral of the field along the surface using outward pointing normal vectors. According to divergence theorem, it's just that triple integral. If you factor out the -2, aren't you left with a volume integral? What's the volume of our cube? Well, those are the dimensions. What's the volume? 8. Outward flux is -16.
Why is it like the two cube? Oh,
Each side has length 2, doesn't it? Length is 2, width is 2, height is 2. I guess it's not really length, width, height. It's technically length, depth, height. Depth is x. Length is y. Height is z.
can we still write out the integral, like what that would be? Is that like,
Each bound would be -1 to 1.
okay, that's what
And then it's just whatever order you want dv to be, right? Because each bound's -1 to 1. That order literally does not matter.
Yeah.
Right, because all the bounds are the same. Yes, because remember, right? Because
when they're in.
that is what the interpretation of a double integral is, right? dA. So that's why I recognized, look, r dr d theta is polar dA. That is a polar area integral. So it's the area of the
Because
domain.
the R is there.
Yes. If the r wasn't there, it would not be a polar area.
Right.
Yes. That's just a triple integral dv, which is a volume by definition. It's fun. Right now, remember how long it took us to do the cube flux before, right? Without divergence theorem. It's a bit longer than that, wasn't it? Wasn't difficult, right? It was just longer. Keep in mind, if instead I said the open cube, right? So the top is removed. You can no longer use divergence theorem. Divergence only works on closed surfaces.
Doesn't that go for all theorems?
So for Stokes and, all right, so technically they work both ways. Right, so yes, Green's theorem is for closed line integrals, but you could also write the double integral as that closed line integral. Now, why you'd want to do that is beyond me, but you theoretically can. As long as you can write the integrand of the double integral as partial of some vector field with respect to x, partial of the y component of some vector field with respect to x, minus the partial of some of the x component of some vector field with respect to y. Same thing with divergence theorem, you can go backwards. Right? If you know that the integrand is the divergence of some vector field, you could just write the triple integral as the closed surface integral. Again, why you'd want to do that, I have no idea. Stokes' theorem is the only one where it is beneficial to go the other way, if you know it's a curl. But yes, the left-hand side of all three theorems are closed. So be careful about that. This works. That actually did work. Impressed. Wait a minute, that's not the right one. Oh, I see. I mixed up the order on my notes. Okay, well, just skip ahead and. Outward flux. Across the cylinder, x squared plus y squared equals 4 between the plane z equals 0 and the paraboloid z equals x squared plus y squared. Oh, wait a minute. Now I see what I did. Each from the wrong one. That's fine. So we'll do another divergence problem and then we'll go back to Stokes. Let's first find divergence. What is the divergence? Remember, divergence is not a vector. Divergence gives you a scalar. How'd you get just x? Okay, so you said partial x of the x, partial y of the y, partial z of the z, right? So it'd be x minus 1. Now I need to describe the region that this surface encloses. Let's go ahead and plot it. All right, so plot all three surface solids. First one, x squared plus y squared is equal to 4. I'm just going to go ahead and do z equals 0. And then z equals x squared plus y squared. Let's see what minus 5 to 5 all the way around looks like. And then, of course, all of my options. Did that when doing the final two. There we go. Right, so the surface if I do that, is it going to give me an error? That's good enough. The surface that we're looking at is the orange, the surface of the cylinder between the blue, the plane, and the parabola, the green. Which means the region that encloses I can get rid of all that. And I'm also going to, at this point, just set Z to be 0, because clearly we don't care about what's under it. Is what's inside the orange but outside the green. Well, the green is inside the orange if you're below here. Right, so all this is the parabola. Or the paraboloid. So we're basically inside here, right? From the green out to the orange. That's what we're looking at as our solid in space. So we have to try and describe that. And just so I don't have to keep flipping back and forth, I'm pasting it here. How do you want to describe this? Do you want to describe it rectangularly, cylindrically, or spherically? The answer is obviously cylindrically. Let's start with Z. So the height goes from 0, right? To the paraboloid. How would you describe the paraboloid in cylindrical? There's Z. R. So distance from the origin to any point in our solid. 0 to 2, right? Theta. Oh, that one's obvious. 0 to 2 pi. Yeah, Z equals x squared plus y squared. Right, so in cylindrical, the paraboloid is defined as Z equals R squared. Right, in cylindrical, the cylinder is described as r squared equals 4, or r equals 2. It's F. Right, outward flux. I guess the first thing you actually should have asked is this a closed surface? And it was.
Something we should have done alongside the problem.
You can determine it just by looking, just by graphing it and looking at it. I didn't in there because obviously it's going to be closed because it's in the set of divergence theorem problems. So clearly. Right, the reason it's closed, right, is because it's bounded below by the plane z equals 0 and above by the paraboloid. Right, so there's no opening. X minus 1 in cylindrical r cosine theta. Then dv is r, dz, dr, d theta. And here is a case, yes.
So why did we put the R there when we were converting dV, but we didn't earlier when it was dA? In the previous problem where you said,
Right, because this was already, I'm parameterizing it as r cosine theta, r sine theta, which means I'm not converting an integral. Right, I'm already setting it up this way.
you also set up.
Right, but it's not a parameterization.
Okay,
It's a description in cylindrical coordinates.
okay.
Right, that's the difference. This is a parameterization. Right, parameterizations are not technically in any kind of coordinate system. It's just how I'm parameterizing it. Right, because it's parameters. I could have used, technically it's UV. Right, that's usually what they use. So instead of r theta, they would have said it's u cosine of v, u sine of v, and then 0. Right? Whereas here, this is a description of a region. When you describe, you have to choose a coordinate system.
If divergence of f gave you like the same thing like x minus 1 and you had to convert, then you would put the r.
Right. Oh, wait.
Like if the divergence was x minus 1 and you had to convert that.
Well, if you're talking about this one, we're not doing divergence, we're doing curl.
Oh, yeah.
Right?
Yeah.
We wouldn't because we're evaluating the curl across the parameterization. So there would be no x, y, z's at all. right? I'd be replacing X with R cosine theta. I'd be replacing Y with R sine theta, and be replacing Z with 0. So the way that's parameterized with the normal vector is already a conversion, right? It already gave me R dr d theta. So it's kind of like I already converted it to polar. That's just how parameterizations work. Yeah, this isn't the only parameterization you could have used, right? I already told you, you could have used x, y, 0, and then your domain would have been x from -3 to 3, y from minus root 9 minus x squared to positive root 9 minus x squared. Your normal vector in that case would have been, I think it would have come out to be 1, 1, 0. What is that? No, it still would have been 0. It would have been 0, 0, 1 instead. And then the double integral would have been set up, like I said, as the double integral of over the domain of just dA. You would have no R, which is this when you convert it into polar. Right, so it all works out in the end. This is actually a example of making a mistake early on and still getting the right answer, as I did in my notes. Because I wrote divergence as y minus 1, which is clearly not correct. But it doesn't cost me, because this part would still integrate out to 0. So I got lucky. We're left with negative R in the integrand. So factor out -1, integrate with respect to theta, just gives you 2 pi. There's no z. So when you integrate with respect to z, you get r squared minus 0. Two pi over 4, pi over 2, negative pi over 2, r to the 4th from 2 to 0 is just 2 to the 4th, which is 16 divided by 2. And that would flux of -8 pi. Let's actually make sure I copy from the right problem set this time.
Remind me how that R cosine theta came out to 0. Is it like the full period thing?
Yep.
Okay, and so how can we tell it's a full period
Of cosine. Right, so I just integrate with respect to theta first. Right, and the reason I can do that is if I distribute the R through, it's R squared, right? And R is not dependent on theta. By the way, neither is Z. If Z was dependent on theta, I couldn't do theta first. Right? What matters is if I were to flip this order, because Z depends on R, I have to do Z before R. When I do theta does not matter. Right? And again, because R does not depend on theta, I don't have to do R before theta. So based on this description, because of how the bounds are, Z has to be before R, but where theta goes does not matter. You can do it first, second, or third, as long as you integrate with respect to Z before doing with respect to R.
I understand why everything else is free.
Because Z depends on R. 0 to R squared, right?
Okay.
Yes. Right, so Z depends on R. But R doesn't depend on theta. And theta, and obviously theta is not dependent on anything.
Okay.
Right. If this wasn't R squared, if this was like to 5, then the order doesn't matter because none of them depend on the others. Now, again, you don't have to do that, right? You can just go with the order that's given. And you'll find out that that part is going to drop out anyway.
So the reasoning behind having a full period of cosine, or different trait, you can kind of just, why can you kind of just eliminate that even though it's like in an integral?
Well, I'm not technically eliminating it. I go, it's going to integrate out to 0. So it doesn't matter.
Okay, and that's
Yes. Because I know, right, if you integrate any periodic function over a multiple of a full period, it's going to be 0. That is a property of integration. So I know because I'm integrating that, right? Because what I'm doing is I'm essentially splitting this without actually writing out. I'm splitting this into 2 integrals. Right? The integral of R cosine theta minus the integral of 1. Right? That integral is going to go to 0. So just, that whole thing just integrates out to 0. I'm done. Right? So it's not really, you're not really dropping it out.
right.
You realize it's just going to integrate out to 0. So just get rid of it
Right.
because it's not going to matter. But that's the reason behind why you can do that, because you can split it into 2 integrals because it's linear. Circulation of the vector field over the boundary of the triangle cut from x plus y plus z equals 1 by the first octant and an orientation of counterclockwise when viewed from above, so positive orientation. So that's the plane, and it's being cut by the first octant. So I'm just going to go ahead and plot those 3. Right, the planes x equals 0, y equals 0, z equals 0. And you know what? For now, first octant, remember, is where X, Y, and Z are all positive. So that's this little bit. Right, lies above the red. There we go. In front of the blue, to the right of the green. So it's this little yellow triangle right here. And obviously C is the boundary of that triangle. So now let me just do this. What I think 0 to, I don't know, 3. See how that looks. And there we go. Which means that yellow is the surface. Now, counterclockwise, when viewed from above, just simply means if we now switch this so we're looking straight down on it. Now it's counterclockwise. Just means set the Z equal to 0 and look at the XY plane. It's counterclockwise in the XY plane. We need to somehow now try and describe that surface. Nope, that's not what I wanted. All right, so again, ultimately, if this was a test question, and I didn't say use Stokes' theorem, you have your pick, right? You can do the 3 paths, right? Parameterize the 3 paths, do your line integral as the sum of those 3. Generally speaking, I find that to be the simpler method. Or you can use Stokes' theorem, which would make us parameterize the surface. Well, this plane has equation Z equals 1 minus X minus Y, right? We can write the surface as Z equals a function G of XY. So I'm going to use as my parameterization. This will give normal vector negative partial of the z component with respect to x, negative partial of the z component with respect to y, and 1. Normal vector is 1, 1, 1. Just make sure that's oriented outward. It is. Right, it's pointing away from the plane. Now we need the parameter domain. So it's the set of all x, y, such that just set z equal to 0. So I'm just replotting the plane, just now z being 0, because I want to plot it in the xy plane to determine its domain. Perfect.
This projector sucks.
I don't think that fixed it. I don't think it made it bold at all. Oh dear, no, that didn't work. 10. No, that's not going to make it bolder either. I really want it to be yellow because that's what the plane was. We're going to use our imaginations. That's gold. Because this screen sucks. And for some reason just doesn't want to display gold as, you know, dark yellow. It wants to display it as like non-existent. Oh, I can't. That's right. It's not going to allow me to do that because it's contour. I'm going to have to do this. thought I could do that. Maybe this. There we go. Use that graph. What's the parameter domain? For what?
X for Y.
Zero to one for both is a square. Which this is not. This is a triangle. Right, so over that region where y extend from, it goes from 0 to the line, right, which is the line y, 1 minus x. So there we go. Oh. Oh, there's one thing I did forget to do. I never found the curl. For Stokes theorem, we need curl. I'm going to be really ticked off if this curl ends up being 0, and I just did all that. I know it's not. Partial y minus partial z. Partial z minus partial x. Partial x minus partial y. So there's that curl. All right, set it up as a surface integral. Now we set up our surface integral as a double integral. All right, remember that means evaluate the curl along the parameterization. X, y stays the same. Z becomes 1 minus x minus y. Yeah, so 2y plus x minus 1, the first component. 1 minus 2x minus y for the second. And then just x minus y for the third. Dotted with the normal vector. dA. Two y minus y is 0. X plus x is 2x minus 2x is 0. Oh my goodness. -1 plus 1 is 0. Circulation is 0. I can't remember if this is the first time I did circulation of a non-conservative vector field being 0. So remember, the fundamental theorem of line integral states if the vector field is conservative, then its circulation is 0. The inverse is not true. I'm sorry, the converse is not true. Just because circulation is 0 does not mean it is conservative. Right? Inverse is also not true. Inverse says non-conservative vector fields have non-zero circulation, which is not true. Which in this case sucks because we just did all that work for no reason. I'm not gonna have time for this one. I don't think I have time for either of them. Eight minutes. Could always start and finish it on Thursday. Circulation of the vector field over the intersection of the cylinder x squared plus y squared equals 4 and the hemisphere x squared plus y squared plus z squared equals 16 for z greater than or equal to 0, oriented counterclockwise when viewed from above. Let's not forget curl this time. Again, we have actually a fairly nice curl. Right? Our curve is the intersection of those two, which is just a circle. The question is, for Stokes' theorem, that boundary serves, or that curve serves as the boundary for what surface? Well, wouldn't it be of the polar cap? The surface of that polar cap? So that's our surface. That's what we have to parameterize. Radius is 4. Right? Since we're dealing with a portion of the sphere of radius 4, for the surface, it's going to be 4 cosine theta sine phi, 4 sine theta sine phi, and 4 cosine phi. I'm also going to write this. I don't know if I'm going to need it. 4s of 1. Now we need the domain. Well, theta is fairly obvious. Theta will go 0 to 2 pi. B, we know, is going to start at 0. Right, and the declination is going to go down to where the two intersect. At the intersection, z squared is going to be 12 because x squared plus y squared is 4. That means z is 2 root 3. Positive because z has to be positive. Cosine phi is root 3 over 2. Because z is 4 cosine of phi. Divide by 4. What is phi? It's pi over 6. Phi goes from 0 to pi over 6. And we are sadly out of time, so that is where we pick up on Thursday. Actually went 2 minutes over. Oh well.
Question. Can you explain again how you got pi over 6 for that?